In this lecture, we are going to deal with pipeline hazards. So what do you mean by pipeline hazard? So when one instruction is dependent on the result of another instruction that is not yet completed, then hazard occurs. That means, for example, you are writing an add instruction, and the result of add instruction will be stored in a register known as R1. So the add instruction will be completely executed only after completing 5 stages, right, in the write back stage. But in the next cycle, you are taking, say, another sub instruction, and in the read, in the first stage, in the second stage itself, you are using R1 as an operand, right? So in the decode stage of sub instruction, you are using R1 as an operand. So in the decode stage, what will happen? You need to read the content of R1 in the sub instruction, but the R1 is not yet calculated because you have only reached the second stage. You have not reached till the end, fifth stage. So R1 is not yet calculated, but you are trying to read from R1 in the next instruction. At that time, pipeline hazard will be occurring because you are trying to read a result of one instruction, but that instruction is not yet completed. We will see one example here. So here you are writing a program like this. So in the add instruction, at the final stage of R1, that is in the write back stage, then only you will be storing back the result of adding R4 and R5 to R1. So in the execute stage, you will be adding R4 and R5. In the final write back stage only, you are writing the result to R1, right? So only in this stage R1 will be updated. But before this, in the second instruction, you are using R1 as an operand. So in the decode stage itself, you need to read from R1, right? In the second function, the second instruction, in the decode stage, all the decode stage, you are reading the source operand. So in the second stage itself, you need to get the result of R1. But the result of R1 is not yet completed, not yet stored back to R1, right? It will be stored back only here, but before that you are going to read from there. So what will happen? Pipeline hazard will occur because R1 is not updated. Similarly, in this instruction, again in the second stage, that is in cycle 4, you are trying to read R1. At this point also you will not be getting the R1. Again pipeline hazard will be occurring, and in these two statements or instruction you will be getting wrong value in and or. But in the sub instruction, you can see that you are taking R1 here, that is in the fifth cycle, right? In the same fifth cycle, you are performing the write operation of R1, but you may think that these two will not be occurring simultaneously, right? But it is not like that way. For the register write and read, it can take place in a same cycle. You can read the actual value itself. Why? Because the write process is occurring in the first half of the cycle. Read process will occur in the next half or the second half of the cycle. So first write process will be completed for R1 in the add instruction, then only the read process will take place, right? So you will be getting correct result for sub alone. Even though write and read is happening in the same cycle, it won't create any hazard. So that is what is told. Even though read and write is occurring in the same cycle, hazard will not be occurring. So except for sub, so sub will be getting correct value, and or will be getting wrong value due to this pipeline hazard. This pipeline hazard is known as read after write pipeline hazard, right? So how will you solve this problem? First method of solving this problem is by inserting no operation instruction. So what you will do, you will be adding two no operation instruction. So what will happen? That means you are wasting two cycles here, so two instructions here. So when the next add is coming, the in the the decode stage will come in the fifth stage itself. So here write process is complete, then you can continue with the read operation. So previous case, after and add, directly you are using add and function, so you will not be getting it here. So what modification you have done? You have added two no operations here. So after two no operation, the third instruction will be your AND. So directly your decode stage will come in coincide with the, or in the decode stage of AND will come in the same stage where the write process is completed for R1. So there will not be any problem. The R1 will be written here. The same R1 you can read here, because read will be done in the second half, write will be done in the first half. So this is one method of solving the hazard problem. But here it will degrade the performance. It is degrading the performance because you are inserting two no operation instructions here. Then these are the two broad categories of pipeline hazards. One is known as data hazard. So data hazard is what we told now. It occurs when an instruction tries to read a register, but that register is not written in the previous instruction. So before generating the result, you are going to read from that register. That is known as data hazard. Second type of hazard is known as control hazard. So in this control hazard, it will occur when the decision of which instruction to be fetched next is not made at the time of fetching, right? So for example, in branch instruction, you are going to branch to a location, another location which is not to the next location in the program. You are going to branch to some other location located somewhere else in the memory. So when you are executing branch in the next instruction, you will not be knowing where to branch or to which address location you need to go. After performing all the 5 stages of branching, then only you will be able to identify the address, right? So here the problem is that you are going to execute a branch instruction, but you don't know where to branch. For getting the branch address, you need to go through certain pipelines. Before that, you are not able to branch. That means we don't know where to branch. So that is known as a control hazard. We will see the example for that later. So next we can see how to solve the data hazard problem. The first solution for solving the data hazard problem was using no-op instruction, but we have already seen that it will degrade the performance. So another technique for solving the data hazard is using a technique known as forwarding technique. So what you are doing in this forwarding technique is that in the previous case, when you are executing this add instruction, your final result will be available only in the write back stage here. From here only you will be giving it to other instructions. But by using the forwarding technique, your actual result, say if you are taking add r1 r4 r5, r4 and r5 will be added and the result will be available after the execution stage itself, that is in the memory stage itself. So by using the forwarding technique, you can forward this result from the memory stage or in the write back stage to the next instruction which requires that. No need of waiting till the end of the write back stage, right? So in the case of forwarding technique, you can forward the result from the memory stage or from the write back stage to the result to the next instruction. No need of waiting till this. For example, here you are using and r8, r1, r3. Here from the memory stage, this is a memory stage, this is a write back stage. From the memory stage before reaching the write back stage, from the memory stage directly you are forwarding it to the next instruction execution stage, right? Directly you are forwarding from the memory stage of first instruction to the execute stage of the next instruction. Directly you are forwarding, and in the next instruction what you are doing, you are forwarding it directly from the before writing into the register. In the write back stage you are directly forwarding into the execution stage of second instruction, right? So by forwarding you can forward the result from the memory stage or from the write back stage to the corresponding next instructions execute stage. So this is known as forwarding. So by forwarding you can solve the pipeline hazard. This is one of the technique. For incorporating the data hazard solving problem by implementing forwarding technique, you need to perform a modification in the control unit, right? Whatever control unit you are having, you need to have a slight modification in that. So this is a modification. You will be adding a hazard unit and two forwarding multiplexers in the control unit. Let us take this as a control unit. Here you are adding a hazard unit and two multiplexers for incorporating this forwarding technique. So what is the use of multiplexer? Multiplexers are added in front of the ALU to select the operand, whether it is coming from the register file in the previous stage, or whether it is coming from the memory stage, or it is coming from the write back stage. Because in forwarding technique, what we have told, before before getting the register from the write back stage, you can get the result even from the memory stage or from the starting of the write back stage. Previously you will be getting the result only after completing the write back stage, but here you will be, by incorporating forwarding technique, you can get or forward the result from the memory stage or from the write back stage. So for incorporating those inputs to the ALU, because finally ALU are performing the operation. So for incorporating the input coming from the memory stage or from the beginning of the write back stage, you are adding two multiplexers for two sources, one multiplexer for one source, second multiplexer for second source. So here you can see three inputs are there. One input is coming from the register file, second input is coming from the write back stage, third input is coming from the memory stage. So by selecting the input to the multiplexer, you can configure any of these three inputs to source A. Similarly, all the three are connected to the source B also. So second register input and the other two. So you can give this to source B also, right? So these two multiplexers will decide which input should be given to the ALU, and that will be decided by the hazard unit. So these are the two multiplexers. And how will you select this input of the multiplexer? How will you select? That is based on these two outputs from the hazard unit. So if this hazard unit output, that is forward BE, is 10, what does it mean? The third input that is coming from the memory, that data will be written to the given to the ALU, right? If B is 0, 1, then the second input, that is the output coming from the write back stage, will be given to the source B. So this selection of the multiplexer input is done by using these two functions, forward B and forward D. So, A. So these two outputs select the inputs in the multiplexer. How you are generating this is based on the match input which is received in the hazard unit, right? So the hazard unit can receive 4 match inputs or 4 match signal, and this match signal, that is match signal 1 M stands for memory. This match input signal to the hazard unit will be set when the source input to RA1E, that is a read address input to this pipeline register, right? You are incorporating a pipeline register between two stages. So if this input to the pipeline register is equal to the data which is coming from the memory stage. So if you are trying to forward the data from the memory stage, right, write address will be same as the write address coming from the memory stage. So if that write address is equal to the input of the ALU, input of the execution stage, then match 1 EM will be set. Similarly, if the address coming from the write back stage is equal to the address or the second address input to the pipeline stage, because each pipeline register will be having two inputs. Why? Because in the previous stage the register file was having two outputs. Similarly, the pipeline stage should also have two inputs. So if the first input is coming from the memory address stage, memory stage, what will happen? Match 1e bit will be set. Similarly, if the first address is coming or first address is equal to the write back stage address, then 1e w will be set. Right? That is for the first address, 1e m and 1e w. Similarly, for the second address, if the second read address is equal to the write address from the memory stage, 2e m will be set, and the second address is equal to the write back stage address, 2e w will be set. So 1e m and 2e m are showing the match input, that is the first register and second register is getting input from the memory address, right? And 1EW and 2EW, it shows that the first register and second register is getting the address which is same as the address of write back stage, right? So based on these four conditions, these four match inputs will be set. Any one of the match input will be set. That match input, so these four is ORed and given to this, or based on these match inputs, the decision will be taken here, right? So how the decision is taking place? So I told four match inputs are given to this. These are the match inputs. Based on the corresponding condition, the corresponding match signals will be set. All these four are ORed together and given here. So then based on that, these two forward signals should be generated. So how this forward signals is generated? If match 1E M and register write M. This register write is an enable for register. So similarly, register write M is an enable. So if register write M and this is both are set, this dot shows the AND operation. If both are set, forward AE will be generating 1 0. 1 0 means what? 1 0 is taking the third input. The third input, it is coming from the memory, right? Memory stage. So if 1e m, that is a memory stage, and the register write, that is a register write for memory stage, if both are set, then forward A is 1 0. That means the ALU will be getting input from the memory stage. Similarly, if match 1e W and register write W, you should see that these both are related with write back. These both are related with the memory. So if both these write back signals are 1, right, then forward AE will be 0 1. 0 1 means what? The write back data will be sent as source to ALU, right? So if both these write back signals are 1, forward AE will be 0 1. So the write back data will be given as source to ALU. If both these conditions are not there, then forward AE will be what? Forward AE will be 0 0. Forward AE 0 0 means then the previous register output will be sent to the ALU, right? So these are related with the source A of ALU. Similarly, these things are the similar things are there for source B, right? So in that case, what you will be taking here for source A input generation, you are taking 1EM and 1EW, right? But for source B generation, what you should take 2EM and 2EW. So you can modify this equation by taking match 2EM and register write M. What will happen? Source B will be selected as selected from the write back stage or from the memory stage. Then 2EW and register write, it will be taken from the register stage. This will be taken from the memory. This will be taken from the register, right? So the same equation can be utilized for generating inputs for source B, right? So the hazard input will be taking input from the register write M and register write W as well as match. Based on these three signals, it will be generating these two forwards or selection lines for this. So how the match signals are setting based on this condition. If RA1E is equal to WA3M, then 1E M match signal will be set. Similarly, RA2E and W3M is set, then 2EM will be set, right? Similarly for the write match registers, and the match signals, and in addition to the write memory and write back register enabled signals, you will be generating forward AE and forward BE, these two signals. So by combining this and register write and register read, you will be generating this. So this is how you are modifying the previous control unit to incorporate forwarding technique. So that is what is explained here, right? So here the hazard unit receives 4 match signals to indicate whether the source registers in the execute. This is a source register. So whether the source register in the execute stage is receiving signal, or if it is matching with the destination register in memory or in the execute stage. So whether these two are matching with these two. So if this is matching with this bit will be set. If this is matching with this bit will be set. Similarly, if the second register read address second input is matching with this will be set. If this is matching with this will be set. So this is the modification made on the control unit in order to incorporate the forwarding technique. Similarly, the other technique for solving the data hazard is pipeline stalling, right? So what do you mean by pipeline stalling? So here you can see this is one load instruction. So in the load instruction, you should keep in mind that it will finish reading the data until the end of memory stage, right? So the result will be available only at the end of the memory stage, right? So for load instruction alone, whatever data you are reading from this memory address, load means you are loading from memory to a register. So this the value will be, the reading will be over only at the end of the memory stage, right? So here only you will be getting the actual data that is read from the memory. But in the second instruction, you can see that in the execute stage you are using the same R1, but so in LDR you will be getting the output only after 4, but at the after 3 itself you are trying to use it. You will be getting the result only after the 4th cycle in LDR, but for the next instruction in the 3rd cycle itself we are going to use. So pipeline hazard will be occurring, right? In this case, forwarding technique will not work, right? Because this is especially for the LDR instruction. For LDR instruction, after the memory stage, then only you will be getting the output. So the forwarding technique will not work. So in this case, you need to use a technique known as stalling, right? So since you are using LDR, you should, so if we say that LDR instruction has 2 cycle latency. So generally, if you are not using the stalling technique, what you should do? You should use the LDR. After 2 cycles only you should give the next instruction. So this is the 2 cycle latency. So if you are using an instruction after 2 cycle, directly you will get the result. Before 2 cycle, if you are trying to execute an instruction, you will be creating pipeline hazard. So this will be overcome by a technique known as pipeline stalling. So this is known as a pipeline stalling. So here what you are doing, you are holding the operation, second operation, until the data is available. The problem was that AND was trying to read R1 here, but you will be getting only R1 here. So before generating the R1, you are trying to take it for the next operation. So here by incorporating a forward a stalling technique, what you have done is you are stalling this RF stage for one more stage in the next stage also. So the same value will be used here, and in the third, in the fifth stage only you are performing the execution. That means you are stalling this stage. So if this stage is stalled, in the third function also you are using R1. So wherever R1 is used, it should be stalled. So this also should be stalled, right? So instead of doing the ALU operation in 4th cycle and the memory operation in the 5th cycle and the register write operation in the 6th cycle, you are stalling this pipeline by one stage. So previously you can see the execution should actually take place in fourth stage, but due to stalling, execution will be taking place only in the fourth stage, and the fifth stage data memory access will be done. But here since it is not shaded, nothing will be done, it will be kept as idle, and only in the sixth stage the write process will be happening, right? So you are stalling this by 1 unit. You are stalling the pipeline by 1 unit, right? So by doing this pipeline stalling, you are adding one bubble state here. This is known as a bubble state. So one bubble state you are adding here. One bubble state will be added here. You can see this bubble state will be added here. Okay, this is known as a bubble stage. It was incorporated due to propagation of this unused stage in this pipeline. So this is known as pipeline stalling. Then for incorporating pipeline stalling, what all changes you need to make in the hazard unit? What all modification you need to make in the hazard unit? So here the hazard unit should examine whether examine the instruction in the execute stage. The hazard unit should execute check the instruction in the execute stage, and if that instruction in the execute stage is LDR, because whenever LDR is executing, then only this stalling will be generally occurring. So what you are doing is the hazard unit will examine whether the instruction in the execute stage is an LDR instruction. If it is an LDR and its destination register matches either with the source operand of the instruction in the decode stage, right? This problem will be occurring only when in the execution stage it is an LDR instruction, and in the next operation you are using this result as an first operand, and here you are using the result as second operand. So this problem will be arising only if in the execution stage you are performing LDR and the operands which you are using in the next instruction, that is a subsequent instruction, are the operands coming out of this LDR, right? So if the operands are taken which is a result of LDR and the execution is LDR, then only this problem arises. So the hazard unit will check whether the execution stage is having LDR and the destination of the LDR, in this case destination of LDR is R1, is if this LDR destination, that is R1, is used as a source operand, used as either of the source operand, because two source operands are there. It will be checking whether the output of the LDR, that is R1, is used as either of the two, either any of the two operands of the next instruction, that is subsequent instruction in the decode stage, right? This is the instruction in this instruction. This is the decode stage of the AND instruction, right? So if the result of LDR is used as source operand to the next instruction in the decode stage, then the stalling will occur, right? Then you should generate the control signals for stalling. So this will be the condition for generating the stalling. If RA1D, that is RA1D is the input to the source, for input to the instruction in the decode stage, RA2D is the second input to the instruction in the decode stage. If these two are equal to output of the LDR, output of the LDR will be this. In the case of LDR, this will be the destination register. So according to the LDR, what will happen? You will be reading a data memory content, and that data memory content should be written to the destination register, right? So destination register is checked by this address. So if the source operands register address, read register address of both the operands are equal to the output of LDR instruction address of the output of LDR, then stalling should happen. So this plus shows you are checking whether OR condition. You are checking whether this is equal to this or this is equal to this. So whether any of the source operand, that is why it is shown matches either of the source operand. So if the either of the source operand of the instruction in the decode stage, right? So this is the instruction in the decode stage, that is the instruction coming after LDR. So whichever instructions source operands are is equal to the output of the LDR instruction, which is coming which is coming in the which is present in the decode stage, then stalling should happen. That is what is done. You are checking whether RA1D is equal to this or RA1D is equal to this. So this will be taken for the decode stage of the second instruction. That you should keep in mind. So if these two are equal, then pipeline hazard will take place. So you need to perform the stalling operation. So if these two are equal, you need to perform the stalling. So how will you perform the stalling? The stalling of a stage is performed by disabling the pipeline register. So the contents will not change. Because if you are stalling this stage, the content of this register should be erased, right? Otherwise, or content of the next pipeline stage register will be erased. It is shown here by disabling the pipeline register so that the contents will not change. Right? When you are performing the stalling, you are changing the here you will be getting a content. That same content you should get here. So you should disable this pipeline register. So for disabling the pipeline register, you need to have some signal, right? So the content will not change. And when a stage is stalled, all the previous stages should also be stalled, right? So if you are stalling one stage, the previous stages also should be stalled, right? So the if you are stalling the decode stage, the previous memories, the previous fetch stage also should be stalled, right? So then pipeline register directly after stalled stage must be cleared. So whichever pipeline register is coming after the stalled stage, that should be cleared. So all these three operations will be done in this circuit diagram. You can see. So here you are having two stall signals. So whenever there is a stall in the execution stage, the hazard unit will generate stall D and stall F signal. So the previous stages will be stalled. So if you are having if you need a stall in the execution stage, previous both the stages should be stalled. So that is done by using these two signals. Similarly, it is told that the register which is coming just after the stalling stage, that should be cleared. That is done by the execution stage. So here what you are trying to do is you are trying to execute an instruction here. So the previous stage should be stalled, right? So what you should do, where the previous stage and the previous stage of that should be stalled, and this pipeline register should be cleared, right? So when the instruction need to be stalled in the execution, whenever it is performing execution, this stage and this stage should be stalled. That is why stall D and stall F signal is given. So it will be stalled, and the stage and the pipeline register which is coming just after the stalling stage, these two will be stalled. So the pipeline stage which is pipeline register which is coming after these two stalls, so that is this pipeline register, it should be flushed. Otherwise the previous data will be there. You need to get only the data coming from the stalled stage to this, right? So by incorporating these three stall signals, you are flushing the pipeline stage which is coming after the stalled stage, and you are stalling the previous two stages. So that is explained here. So if RA1D is equal to RA3D 3 or RA2D is equal to WA3D, then match signal will be generated. If this match signal and memory to register E, where is it? Memory to register E. If both these signals are set, then stalling will done, because memory to register will be generating or it will be generating, or it will be sending the data to the register file. Memory to register signal is the register which will select any one of data to the register file. So if this is set, then only the load operation will take place, right? So if provided if this bit is set and the match bit is set, LDR stall operation will take place. If LDR stall operation is taking place, stall F, stall D and flash E, all the three signals will be signaled or asserted, right? So the all these three operation will take place when the match operation is this match signal is set and memory to write E register, that is this memory to write, because this signal is used for loading the result to the file register. So loading will happen only if this is set, right? So if the match bit is set and this bit is set, LDR stall will happen. When LDR stall is happening, all these three bits will be set. This is how we are modifying the control unit of the hazard unit. So these are the details regarding data hazards. In this lecture, we are going to deal with the control hazards. So control hazard will occur when executing a branch instruction and the pipeline processor does not know where to branch, right? You are having an instruction and the instruction don't know, you are having a branch instruction, the branch instruction don't know where to go, because that will be calculated only after executing 4 stages. So for example, this one you can say branch 3C. So this 3C will be only available only at the 4th stage. After completing 4 stages, then only the processor will be getting this address, right? So the next instruction which I have taken has gone through fetch stage, decode stage, execute stage and memory execute stage and memory stage. Like that, in each cycle each instruction may have taken. So after 4 stages only you will be getting the address. By that time, 4 instructions may have been filled the pipeline, right? So what will happen, you need to actually move from this address to this address. So when you are moving from here to here after execution, these 4 stages may have been taken, that should be flushed out, right? That is a problem related with the control hazard. So whenever you are having a branch instruction, next 4 instructions should be flushed out. So 4 instruction you have wasted, then only it will be going to the actual instruction which is written here and instruction. Why? Because you will be getting the address only after 4 stages, right? So 4 instruction need to be flushed out. So how can you reduce this branch prediction penalty? This is known as a branch prediction penalty, because what do you mean by branch prediction penalty? You thought that this may be executed in the next cycle, this instruction. So you have gone there. Then you have subsequently you have you have taken all these 4 instruction in the pipeline, but only after 4 stages you identified that whatever instruction I have taken is wrong, you should go to only this instruction, right? So when you are moving from here to here, you have made a mistake in trying to execute 4 instruction, then you will be getting a penalty known as misprediction penalty. So here my misprediction penalty is that I need to flush 4 instruction. So how can you reduce this? So this misprediction penalty can be reduced by predicting the branch just after the execute stage itself. So if you are able to predict the branch just after the execute stage, your number of flushing can be reduced, right? You can see here. So here you are able to get the branch address in the execute stage. So you will be getting the branch address after 2 itself. Before entering 3, after 2 itself we are getting. So only 2 instructions you need to flush out, because in the next instruction itself you will get the address. In the third cycle itself you will get the address. So here only 2 instructions you need to flush out. In the previous case you need to flush out 4 instructions, but since you are predicting the branch after the execute stage itself, that means you are performing the branch prediction earlier, just after the execute stage, you are able to reduce the branch prediction penalty by 2. only 2 instruction has to be fleshed out rather than 4, right? So how will you incorporate this earlier prediction or earlier branch prediction in the control unit? That is what you are going to see now. So here, for incorporating the earlier branch prediction, again you are modifying the hazard unit, right? How are you going to modify the hazard unit? You are adding one multiplexer here, right, which will give the branch prediction address just after the execution stage. Previously you will be getting the branch prediction address only after the write back stage, or only after the read memory. Generally only after the read memory stage you will be getting the branch prediction address, right? But now you are adding one more multiplexer here which can take input after the execution stage. So here after the execution stage itself you will get the actual branch address. That branch address will be taken from here and should be given to the PC for branching operation. So for giving that input also to the PC, you are adding one more multiplexer here, and this multiplexer is controlled by branch taken E control signal, right? So you are adding one more address, one more signal known as branch prediction E, branch taken E. So branch signal will be used for generating that signal. So if it is a branching operation, this bit will be set as 0. This bit will be set as 1. So the output from the ALU or output from the execution unit can be directly fed into the PC without feeding the output of memory stage. You can feed the input, you can feed the output from the execution stage to the PC using the signal. So these two are the modifications you have made in the hazard unit in order to incorporate something known as uh, the earlier branch prediction. So for earlier branch prediction, you are using this signal and one additional multiplexer. One additional multiplexer and one branch signal. These two you are adding.